So what I want to highlight down here, right? If it's at a specific point, like x is equal to 0, x equal to a, x equal to l minus a, x equal to l, right? They are all going to be constant. Okay, so they are all, so this is a constant. Over here, this is a constant. So the magnitude that you find on here at all the specific point are going to be constant. Okay. A to B, because it's ranging, is going to be equation. Okay. So it means there will be the magnitude will vary. Okay, the magnitude will vary. So it's going to be a function of x. Okay. Okay. So we know that you're going to have 4 constants and 3 equations times 2. So we have 7 points, 7 section 1, 2, 3, 4, 5, 6, 7. 7 times 2, you're going to have 14 equations. Okay, or 14 expressions. Okay. So now let's look at point A. Okay, at point A. So the first one is at point A. Okay, so at point A is where x is equal to 0. Okay, so I'm going to draw a very finitely thin beam. Okay, that's our beam. And over here we have a load P. Okay, and then we have our geometric datum. And this distance is our x. We know x is equal to 0. And we are going to assume positive shear and positive bending moment. So V as a function of x, and this is M as a function of x. When I was undergrad, I always ask myself why V as a function of x is not going up. Sorry, at this point that we find it's not V as a function of x, it's at VA. Okay. I ask myself why VA is not pointing upwards to resist the load P. Okay, it was bothering me. And then later on, when I started teaching this course, okay, so over years, you can imagine, okay, my prof did not tell me anything. I realized why is that? Because we are making the assumption of what? Like how I started, we are making the assumption of positive shear and positive what? Bending moment. That is why the forces, the shear force and the moment are going this way. Okay? So don't be like me, discover it so late, discover when you're young. So for this case, we know that we're going to do static analysis. So positive is going up. Okay, summation of forces in the y direction is equal to 0. So we have minus P minus V as at point A is equal to 0. So V at point A is equal to minus P. Okay, and then we do moment. So we do summation of moment. In the z direction at point A. So point A, we have force multiplied by 0 distance. So moment at point A is equal to 0. Okay, there is no perpendicular distance. Okay, I write down why it's equal to 0. No perpendicular distance. Okay, so now you go back to your table to write that this is minus P. This is equal to what? 0. Okay. So next we're going to do from A to B. So these are still the easy ones. Okay. So let's go from A to B. So it's 0, X to A. Okay. So I'm going to draw the beam now. So we are aware that we have a load P down here, right? Geometric datum is still over here, did not move. Now this is we have a certain distance X, right? Now because we have a distance which is X ranging from 0 to A, our shear force is V as a function of X and moment as a function of X. Okay. Then the same thing we do static analysis. Right? So we do summation about forces going up is equal to 0. So this is minus P minus V as a function of X is equal to 0. So V as a function of X is going to be constant. It's going to be a P. That's the expression. Okay. Remember now it's V as a function of X. Then we do moment. So what shear? Okay. So we are going to do summation about moment in the Z direction at point X is equal to 0. So what this means is we are doing the moment where I'm putting the red dot. Can you all see the red dot? That's where we are taking our moment. Not at the datum, but at the red dot. Okay, that's where we take our moment. So when that's the case, now we have P over X, P multiplied by X, which is a constant, right? So it's going positive, Px, not P as a function, sorry, Px plus by M as a function of X is equal to 0. Okay. So what we have is M as a function of X is equal to minus Px. Okay. So now we realize that it's a variable now, right? This is not the M as a function of X. It's not a constant anymore. So as the distance increases, the moment increases. Okay. So back into our table. I do apologize. Maybe this is best where we write V at point A is equal to minus P. M at point A. This will be equal to 0. Okay. So now you have Vx. So the limits is 0 to A. So this is still minus P. M as a function of X now is equal to minus Px. Okay. Okay. So we just put things onto your table. Then the next one, we are going to find at point B. Okay. At point B, where you have X is equal to A. Yeah. Okay. So now X is equal to A. Okay. So geometric datum is over here. Now this is P, right? And this is at point B. So this is our point A. Our point B now. Now at point B, we have a reaction down here. And that reaction we calculated is equal to is equal to P plus by omega over 2. Okay. So P plus by omega over 2 L minus 2A. Okay. You have to include this reaction force, because this is exactly at point B, right? This is exactly at point B. So we have our shear force, positive shear assumption, V at point B. And then we have moment at point B. Okay. So now we carry out a static analysis again. Today I'm spelling static in a weird way, okay? Static analysis. Okay. Positive is going up, summation about forces in the y direction. 0. So you have minus P plus by P plus by omega over 2 L minus 2A, right? Then minus V at point B is equal to 0. Okay, so these two will cancel out. So V at point B will be equal to omega over 2 L minus 2A. Okay, so that is your shear force at point B. Okay, then we go to our bending moment. Summation of moment, the Z at point B, okay, equal to 0. So now again, I will repeat myself. We are taking moment at the red dot. Okay, so you will always remember. Okay, so we know that the distance from here to here now is A, right? So now we have P multiplied by A. Okay, any other moment, that's it, because P plus by omega over 2, this term over here does not have a perpendicular distance, plus by moment at point B is equal to 0. So moment at point B is equal to minus PA. Okay, so moment at point B is equal to minus PA. So coming back to our equation, the shear force at point B will be equal to omega over 2 bracket L minus 2A. And then M, moment at point B, is equal to, is it equal to minus PA? Let me check. Yep, equal to minus PA. Okay, I'm going to stop forming the equation down here. Okay, and I'm going to sketch. Okay, we are going to sketch the shear force and bending moment equation. Okay, we're going to sketch the shear force and bending moment equation. So I'm going to go into graphing. Okay, and I'm also going to explain why the geometric datum is on the left hand side. Okay, I'm going to explain why the geometric datum. Only after when we draw the shear force and bending moment equation, then we know why the geometric datum always have to be on the left hand side of the structure. Okay, as I say, you can move it, but mathematically you have to be very, very strong to compensate the translation. Okay, I will not do it. Okay, because I will have to focus on the physics, and my math is not strong enough. I'll tell you this. Okay. So this is X. This is V. So this is our shear force diagram, and then I'm going to label this at 0. Over here is our point A. Over here is our L minus A. And over here, exactly at the end, is our point A.